actually Yaroslav Vinitsky, who was already mentioned but who cannot participate, still is present here, so to say, because he is one of the co-authors of this our presentation. So I would like to talk about some interesting processes which involve two types of systems: long flexible polymer macromolecules and some small particles which can be organic or inorganic nature, considered as some defects or pollutants. In such a case, this process have very closely related to interesting processes which are important in ecology and, for example, cleaning the wastewaters from some, for example, high ions pollutants. And there is interesting process which is called flocculation. What does it mean? So we have some pollutants in solvent, which can be of either nature, and we have long flexible polymer macromolecules which can adsorb these particles, these pollutants, in such a way that some so-called flocculation bridges, just some adsorption occurs. So in such a way, we can remove these particles which are adsorbed from solvent. This is kind of filtration. So when this aggregates polymer macromolecules with adsorbed particles, they are called flocks, these aggregates. That is why this process is usually referred to as flocculation, which is more, there is some evidence, experimental evidence, that it is more effective to use in such process not just linear polymers, as it is schematically presented here, but some polymers of more complex so-called branch structure. For example, the simplest representative of such branch structure are so-called star polymer. So star polymer consists of some number, say here it is presented the case F equal 5 linear branches, which have common starting points, so to say. So why these polymers seems to be more effective? Because we can intuitively see they have some dense regions around this central point. They have reduction of branch entanglements because these branches of star polymers are in some sense separated from each other. So what actually we are interested in this study, we consider the set of so-called core shell-like polymer structures. So we use some what is core shell? Is some kind of carrier, so to say, some central core, which can be of either dimensionality and either form, so to say. But in the simplest case, we can consider some point-like central core, or we can consider one-dimensional rod-like cores. And then some amount of linear polymer chains are grafted to this core. For example, if we have a point-like core, central core, and we are grafting some amount of linear chains, so we actually restore what was presented here, this star-like structure, yes? And if we take rod-like core, and again, we graft some number of linear chains. So here also we can introduce some separation length, which is denoted here as S large. So this is separation between two grafting points. Then what we receive as a result, in polymer science, they are known as complex structure. Complex structure. So we will consider star-like structure and complex structure. And so F is number of these linear chains which are grafted, and N large is the length or molecular mass of each of these linear chains. So the total molecular weight of such complex structure is just F times N. We will use computer simulation, actually, which is based on very simple lattice model representation of polymer structure. Let us start with modeling star-like structures, which are presented here. For example, here we are considering two-dimensional lattice, but actually, in fact, our results, which will be presented in follows, will be for more realistic three-dimensional case. So just to give you some impression how this lattice model works. So we start with putting this central core, just some point-like core somewhere in the center of our lattice. And then we applied so-called polymer chain growth algorithm to build actually some desired number of polymer chains. For example, here we consider three these branches of star polymer, which are grown step by step. So for example, this is our zero state. We just have the central core. Just we put three monomers in some randomly chosen nearest neighbor site of this central core. So this is our first stage. Then the next stage. So again, the second monomer is added. And so on. This is how our star polymer is growing step by step. And in the same way, a little bit more complicated, we can construct this complex structure when we have a central core in shape of some rigid rod, presented here as with red color, with red symbols. And for example, we are interested to have two grafted chains to this central rod at distance s equal 2 between them. So this is one starting point, this is another starting point. And again, step by step, by randomly choosing next available random site as nearest neighbor site of previous one, this is how our complex structure is growing. So finally, what we receive, this is snapshot of our simulation, is something which is presented here. So this is star-like structure. With red color, we are showing this central core, which has just the shape of it's point-like. And here we have complex structure with central core in shape of rigid rod. So this is star-like structure with three arms, three linear chains. This is complex structure, again with three arms, but they are now separated. Their starting point are separated by some distance, say 4. So what we are interested in, this structure will serve as flocculants for adsorbing some pollutants from solution. But first of all, let us analyze a little bit efficiency of this structure. So what we are considering here, so this is a presentation of one of the branch of either star-like or complex structure, which has length n. And we are interested to analyze such quantity as, let us call it accessibility. So what does it mean? So we see that in our lattice, around each monomer of this branch, there are some amount of free lattice sites which are not occupied by another monomers, and it means they will be allowed in what follows for this pollutant particle to adsorb. So this is like potential points, potential spaces for pollutant particles to be adsorbed to these monomers. So, and it's interesting to consider so we introduce some numbering from, this is first monomer of this branch, this is the last monomer of the branch, there are n totally of them. And we can compare, for example, star-like structure and complex structure. For star-like structure, of course, we can immediately intuitively see from how it looks like. These monomers, which are very close to the central, to this core, because there is this crowdness effect, so to say. So these monomers have very bad efficiency. The accessibility is very low, and actually it decreases with increasing the number of branches. So the more is this amount of these grafted chains, this is not good for accessibility because they create some crowdness effect to each other. But for complex structure, as far as they are separated from each other, well, it is intuitively clear, but it's interesting just to describe it quantitatively. We can immediately see even from this picture that complex structure would be much more efficient in catching particles from solution. And so here we can estimate in more detail this average accessibility of complex structure and star-like structure in comparedness. So here, just to give you more ideas, what exactly quantities do we mean? For example, we have star-like structure. This is our central core. And each branch has only one monomer. So this accessibility means for each of the monomer means 5 in three-dimensional lattice. This accessibility, of course, decreases when length of chain increases because they interrupt each other. Yes, they have this crowdedness effect close to central core. And in contrast, when we have complex structure, since these branches are separated in space, accessibility is much better than for star-like structure. This is really what we receive here. Star-like structure with number of branches starting from 1. 1 is just a single linear polymer chain, and it grows from 0, say, to 5. And complex structure, again, 1 corresponds just to simple linear polymer chain, and this number of grafted chain is growing from 1 till 5. So we can see how much more efficient is complex structure comparing with star-like one. And also what is important in the case of complex structure is that we have additionally this separation between starting point of grafting chains, which also plays important role. So when this separation equal to 0, actually we just restore the star-like structure. When this S increases, so it means, of course, this distance between grafting points increases in space. And it should not be increased, of course, till infinity, because actually we can estimate this separation. When the separation is large enough, we will end up just with set of linear chains which almost do not feel the presence of each other. So actually it was rather some introductory analysis of these two structures, comp-like and star-like structure, because actually our main task is as following. We are interested in peculiarities of adsorption process of these two structures in solvent when we have some amount of pollutant particles dissolved, and our task is to adsorb as much this particle as we can, so and analyze which of these structures are more efficient. So within our lattice model, how it works, we construct this structure, star-like and complex structure, and immerse them into solution with some amount of particles. And then in such a case that these pollutant particles occupies the next nearest neighbor position of site which is occupied by monomer, it means it is adsorbed. So the main quantity we are interested in is what average number of obstacles can be actually adsorbed by a given polymer structure. Total means total molecular mass, total number of monomers of this structure, and it should be somehow I did not mention, we also introduce concentration of these particles, of course. It should be probably introduced a bit later. So let Na be the average number of particles which are adsorbed by polymer structure. And we introduce a normalized value, Na small. So it's number of adsorbed particles divided by molecular mass of polymer structure. So we call this adsorption capacity per one monomer. So the larger is this quantity, it means on average the more powerful is given polymer structure is in adsorbing some amount of particles from solvent. So how this quantity look like? We have them here. So this is adsorption capacity, and total is total number of monomers in polymer structure. For comparing a star-like structure with zero central core and complex structure with rod-like central core. Again, let me remind you, F equal 1 is just simple linear polymer chain, and the larger is F, the more grafted chains we have. So if we, first of all, what we can notice here, that in the case when we have very short these branches, they are more effective. First of all, because of the shorter is branches, the smaller is this crowdedness effects. The more open are these branches to absorb new particles. And this quantity gradually reaches some saturation value when total number of total molecular weight of our considered polymer structure increases. What is more important to notice here that we can see that star polymer structure are not so efficient in catching, absorbing particles. So, so this lower curve here actually corresponds to star-like structure with 5 maximum number of branching points. On the opposite, complex structure are very efficient. And this upper curve actually corresponds to complex structure with 5. So it looks like here we have 5 these grafting chains. And also, as it is probably expected, if we change the separation between grafting points, so again, we change it starting from 0. 0 corresponds just to star-like structure, and we gradually increase. And again, of course, we can follow how adsorption capacity is growing with increasing this separation. So the mostly effective from point of view of adsorption capacity are complex structure with maximum separation between grafting points. But this is not the only quantity which is of interest in such adsorption processes. We can introduce another quantity which we called adsorption strengths. So what does it mean? Is the average number of chelation bonds per one single adsorbed particle. So I don't know. It is just presented here. So if we have some particle, this pollutant particle shown here with blue symbol, so green corresponds to monomers of each polymer branch. So it is clear that each particle can create more than one bond, can be 1, 2, or 3, or even more, with monomers of polymer structure. So actually we are interested what is the average number of such bonds in the case of different topologies of these polymer flocculants. And again, why it is interesting? Because the larger is this average number of bonds which adsorbed particle established with polymer flocculants, the more stable is this adsorption process. Because if we consider situation when these bonds are not infinite, they can be broken with time. So it's much better and much safer if these adsorbing particles establish more than one bonds. So again, we consider this quantity, average number of these bonds established between single pollutant particles and branches of polymer structure, as function again of total molecular weight at different values of grafted chains. Again, we started with F equal 1 is just one single chain. We have star-like structure and comb-like structure. And what is interesting here is that behavior is completely opposite as it was when we considered adsorption capacity. So while star structure were found the less efficient in catching adsorption, in catching the pollutant particles, in opposite, star-like structure are found the mostly effective from point of view of establishing this connection. So the average number of hilation bonds actually are maximum for star-like structure and the smallest for complex structures. It is actually maybe to understand in more details why it happens like that. Let us consider another interesting process here. Let us evaluate the average number of these adsorption bridges between different chains, different grafted chains. So what do we have here? We have for compareness star-like structure with 3 branches and comb-like structure. So with red we show the central core with 2 branches. So as we already mentioned, each pollutant particle can establish one or more bonds with monomers of polymer structures. But another interesting question, are these bonds are established with monomers which belong to the same branch or to different branch? For example, here we have particle shown with blue, which establish 2 bonds with monomers which belong to the same branch. Yes, and here we have particle, again, it has established 2 bonds, but with 2 different branches. And so what we have here, we have probability probability for pollutant particle to establish bond with some number G, which can be 1, 2, or more. This is number of different branches. So again, S equal 1 correspond to star-like structure, this one. We can see that in the case of star-like structure, because of this crowdedness effects of monomers close to the central point, we can see that maximum, mostly probable for pollutant particle to establish bonds simultaneously with 2 different branches. Also, simultaneous bonds even with 3 branches is still not 0. Still, it's very small, but still is possible. On the other hand, when we consider complex structure, it means when S starts to increase, this situation drastically changes. And in this case, it's a probability for a pollutant particle to connect 2 or more different branches. Actually, it decreases very quickly. And in this case, mostly probably pollutant particle will establish bond only with monomers of the same branch. Also, in the second part of this our investigation, we considered process of dynamics. So this first one, we considered actually. So I did not mention, I guess. We considered the case of so-called frozen disorder. So we consider the situation when this, it's kind of like suspension, we can say. So these particles are assumed not to move. Actually, they are just frozen in space. And here, mostly probably interesting in the case when these particles are allowed to diffuse, actually. So they are diffusing and gradually they aggregate more and more with time on this our polymer structure, this our flocculants, until some saturation is, the regime of saturation is reached. So actually, as it is expected here, again, we are interested in two main quantities. First one is adsorption capacity. It's average number of particles which are adsorbed to polymer structure. And another quantity is average number of bonds established between pollutant particles and monomer of polymer structure, but now it is with time. And as expected, these quantities are reaching some saturation values with time, which is interesting here that while for adsorption capacity we see very gradual behavior, these quantities are just increasing with time until they reach some plateau. So actually several cases of star-like and complex structure are shown here also. And this more interesting is behavior of average number of bonds established between pollutant particles and polymer structures. They have some minimums, they are increasing again, and there are, if go into more details, there are some interesting effects that first of all, these pollutant particles can reach mostly open, so to say, monomers with high accessibility. And this process is a bit not trivial with time. Again, the main tendency in the case of diffusive particles actually are the same like we discussed before, and the main finding actually is that star-like structure are more effective in establishing more than one chelation bonds with pollutant particles, while complex structure are more effective in actually absorbing so much particle as possible. And the last quantity which is of interest is actually this saturation time. So which time is needed for different polymer structure to reach the saturation regime when pollutant particles maximally adsorbed. And again, as it is probably intuitively expected, complex structures, since they have high accessibility, they are more open in space. So the saturation time is actually much smaller. So this process reaches saturation much more faster for complex structure, while for star-like structure it takes more and more time with increasing number of grafting chains. So actually, to conclude, I wanted to present some findings of peculiarities of adsorption processes of pollutant particles on a set of different complex polymer structure. As an example, we considered star-like and complex structure. And what is the main findings? That star-like structure are found to be more efficient from point of view of adsorption strengths. So they can establish more bonds with pollutant particles comparing with complex structure. In the opposite, a complex structure are more effective in adsorption capacity. So they are able to adsorb effectively a larger amount of particles of pollutant comparing with starting structure. So this is main result which I wanted to present.
Thank you very much. Let's thank our speaker. And now we are open for questions. Please, if you have questions, you can ask. No,
Maybe.
yes, please, Taras.
Maybe it's just the question of the term chosen by you, Victoria, but it sounds a bit strange when you see that obstacle can diffuse.
Diffusive particles, yes.
There is assumption of obstacles on something. When I imagine an obstacle, it's something unmovable. I understand it's kind of an abstract model, and but obstacles usually they don't move.
Yes, maybe. Yes, in this case, really, it's better to use not obstacle, but actually, we did not think about that. So yes, because it is like first part of study, we considered them like frozen, and then we decided to let them to diffuse in space. Yes, better to use pollutant probably, pollutants.
Another question. So pollutant, what is it? Pollutant? You're tending to describe some pollutants, and what is it? Biological pollutants or some chemicals? Or what is it actually?
So actually, we assumed rather chemical, yes. Chemicals.
For example, what is it? It is macromolecules. Is it colloids, or is it polymers, or it is metal ions?
Well, it was actually somewhere at the beginning I mentioned very shortly some related experimental situations, so to say. Yes, so originally our interest toward this study was related to problems of wastewater, cleaning of wastewater, for example, from mercury ions, kind of that.
One moment, technical problem. What was it was not completely clear for me. So, is that model two-dimensional or three-dimensional? It is.
No, it's actually three-dimensional. It's three-dimensional. Just here I showed just for convenience. But yeah, this is our real snapshots. This is three-dimensional. This is snapshots of our simulation. Yes, it's three-dimensional.
But it looks like in one plane or everything here at this picture. Just you rotate some direction.
In some picture.
No, it's actually three-dimensional. Yes, yes, it's three-dimensional.
So 6 bonds can appear there, right? Not just so.
Sorry, what was the question?
So how many bonds can appear between particles?
How many bonds? I think it's maximum 6.
6.
Yes, because yes, maybe of course it's very rare event, but it's possible.
So if it is something real, it kind of valence bonds or covalent bonds or something.
No, it's of course it's another question how it can be physically, but just in terms of our lattice model, of course it can be 6. Okay. Another question, we can introduce restrictions with hands really to make it more physically reliable. We can introduce restriction can be maximum 3 or 4, depends on what is our target.
Okay, thank you.
Victoria, thank you. And I also wanted to ask probably something not so complicated. In this model that you show, you have never winded chains. So is it possible in the model, for instance, in branched polymer, when you have some center, core, and also branches, these branches can wind around each other? Or not? You do not show this this situation, but in general it is possible.
But I think it was not excluded. You mean?
I mean,
just they cannot intersect each other.
But you mentioned that near the core we have crowded place. Yes. But
yes, just because they are very yes.
Yes, but if we allow these branches to wind around each other and form some aggregates, for instance, we will have more space, so not so crowded space. And I mean that this mechanism may be present in this system, but maybe this is not the case. I don't know.
It's only special, how to say, effects of space, yes. Just these monomers are close to each other, so it means there is not so much space for particles.
Space may be entropy of the system.
But also this is problem of lattice model. In continuous space, it would be, I guess, not so much pronounced, this effect of crowdedness. This is mostly effect caused by lattice structure.
I see. Okay.